Okay, so we're going to exploit the memory hierarchy, and we're going to have this notion of, well, we have a small fast thing and a medium-sized memory and then a very slow but very large memory off on the hard disk. And we're going to use this hierarchy. So what's the trick? What's the trick? If I'm accessing a certain set of locations a lot, where should those locations live? In the fast memory. And everybody else can go live in slow memory, and only when I access them the first time, what am I going to do? I'm going to move them into the fast memory so I can get to them there. And eventually the fast memory gets full, and what should I do then?
Get rid of the oldest stuff?
Get rid of something. What should I get rid of? When you open your refrigerator back at the dorm, and you go, oh my God, and you say, well, I got to put stuff in the new keg of beer, what do you throw away? Yeah, the old keg of beer. What you have to do is you sort of you have a replacement strategy. You pick something that you probably say, if I throw it away, I won't miss it very much.
Sentient leftovers.
Yes, sentient leftovers. I like that idea. Okay, so that's the basic scheme, right? We're going to try to put the things we want to access into the small fast memories. Now, there's two basic strategies we could pursue. We could, I'm still thinking about sentient leftovers. The two basic strategies I could pursue. One is I could, this is the thing hardware types love to do. SMOP. Everybody know what SMOP means? S-M-O-P. A small matter of programming. Right, and so us hardware types who are lazy basically say, oh, the program guys, they'll figure it out. So what I'll do is I'll just build this hierarchy, right, and I'll just tell you to put, it'd be up to you to, if you want your program to run faster, you should devote some instructions to moving the things you want into fast memory. It's up to you to figure it out. You'll know better than me. Right? And that was the approach that was advocated by Seymour Cray when he built his fancy vector machines, which for many decades were the fastest machines on Earth. He basically had these very fast pieces of memory that would hold the vectors, and it was up to the programmer to figure out how to load the vector registers and then how to use them. And his famous sort of speech about this was, look, you don't have a large fast memory, you have a small fast memory, and you can't fake what you haven't got. Okay, well, Seymour was very clever, and in fact, quite remarkably, over the span of several decades, his machines they held the speed record. They were always the fastest machines on Earth. So this was a man who sort of knew what he was talking about when it came to circuit design and computer architecture. However, this is one occasion where I think Seymour was wrong. Okay, as it turns out, we can fake what we haven't got, and that's because we're behaving rationally. It is possible for us to build hardware that will automatically manage where a particular memory location can be found. Okay, where you don't have to think about it. So you just access memory like you normally would, using addresses that your program generates. And the hardware will sort of look over your shoulder and say, I see what you're doing. You're starting to read from the foo routine. Maybe I'll get the rest of the instructions of the foo subroutine into fast memory, into a fast program memory. And when you ask me for them, I'll already have them. How clever. Right, so the machine could take advantage of the fact that there's some systematic patterns to our accesses and then do a good job of doing this automatic memory management. And what I want to spend the rest of this lecture and the next lecture doing is we're going to look at the details of how that hardware works and why it works. Okay, it's sort of fun, actually. It's sort of neat to imagine that we can actually, solve this riddle, that we can get something where our machine really does work at 1 billion instructions per second. It actually needs a new instruction every nanosecond. Okay? Yet our main memory system isn't capable of producing a new instruction, randomly, anywhere near that fast. Somehow it all comes together and works. So we want to understand that hardware. Okay. So if we ask for a particular memory location X, the hardware will actually first look in its little cache. That's going to be our name for this small fast memory. And it will see if is that address something that I've already sort of thought you'd asked for and I have in memory, or that you previously asked for but not very long ago, so I haven't taken it out of the refrigerator yet. It's not sentient. So, sorry. you look at this and you say, okay, first I look in my cache. If I don't have it there, then I'm going to have to go look in the main memory. And in fact, in most modern systems, when you start a program, it doesn't bother to read the program off of your disk storage and put it into dynamic RAM. It just leaves it on the disk, and only the first time you access it, it gets so-called paged into main memory, and then from main memory into the cache. So there's this sort of a combination of hardware and software that is going to automatically manage getting your program and your data, your instructions and your data, into the storage level of the storage hierarchy where they should be at any given moment. And by and large, if we do this well, mostly when we ask for an address, more than 95 or 96% of the time, we'll be able to find that information in that static cache. Any questions about the basic plan? Now you can say to yourself, well, I see a big CPU and the small yellow box labeled cache. The reality of the situation is the proportions are a little different. If you opened up the Intel chip that you have and looked at where it put its transistor budget, most of the several billion transistors that you've bought are actually in the yellow box. Okay, most of what you buy is cache memory. So the size of the cache is important, and the faster you want your computer to run faster, it's not so much you have to make the CPU faster, you have to make sure that on the average you're finding more and more and more information in the yellow box. And the way we do that is by making the yellow box be able to hold more and more bits. So the real key to performance in most systems in the modern world is large amounts of cache. And in fact, in the sort of memory, the computer chips that you have, there's actually 3 levels of hierarchy of the yellow boxes. Okay, so there's increasingly larger but slightly, but a factor of 2 smaller cache systems, and there's a stack of those even before you get to the main memory. So this hierarchy idea really works, and we've done a lot of engineering in the modern chips to sort of deliver it to you in the most tasteful form. For our purposes, we're going to imagine a single layer of yellow box.